Hi everyone, welcome back. If you haven't already done so, hit the subscribe button right now. For the past half a dozen videos or so, we have been looking at object detection using a couple different approaches. In fact, in the last 3 videos, I covered the topic of object segmentation in scientific images using an approach called star dist. If you don't know what in the world I'm talking about, I definitely recommend you to go back and watch those videos. You may find them to be useful, especially if you're into object detection in scientific images. Now, in the last few videos, while I was talking about object detection, many of you reached out to me and asked for mask RCNN, and there you go. That's why I'm back here. And the plan here is to talk about mask RCNN in this specific video, in this specific tutorial, and in the next one, walk you through the process of installing mask RCNN. It can be a little bit of painful process, but I believe 90% of the challenge when it comes to mask RCNN comes from installation. But once you have a working environment, then everything else is easy. So the video after that, we are going to cover the topic of training and performing object detection using a data set that already exists. Someone already annotated that. And this, let's look into Kaggle to actually download that. And to be frank with you, I haven't gotten that far. I just tested how to install it, and I got super excited that I got an environment that runs mask RCNN, and I hope I can repeat it in my next video. And any issues that I run into, I want you to see. So I'll record every step and go through any troubleshooting process. So please be patient when you watch the next video. Okay, hopefully we don't run into a lot of issues. The one after that, the final video, let's go ahead and download some random images from Google, annotate them using one of the annotation tools to create your labels and images in the right format that are appropriate for mask RCNN. That is the plan. So let's go ahead and start understanding what it is at a relatively high level, and then slowly get into the coding part in the next video. I hope you like the plan. So let's go ahead and continue. The CNN in mask RCNN stands for convolutional neural networks, as many of you probably know. And RCNN is basically a region-based convolutional network. So we're getting the terminology straightened out right now. Faster RCNN, it's faster region-based convolutional neural network, and in between R and faster, there indeed is something called fast RCNN. I'll also mention exactly what that is. And finally, mask RCNN stands for mask region-based convolutional network, and I put faster in the parenthesis right there because mask RCNN is based on faster RCNN. So let's go ahead and progressively address each of these and see how these different algorithms actually work from a practical point of view, and then eventually end with mask RCNN. So CNN, convolutional neural network. I did many videos on this topic. In fact, we have used convolutional neural networks quite a bit. All of our units are convolutional neural networks. Most of the classification that we have done in at least on my channel, these are all based on convolutional neural networks, and these are amazing for classification type of problems. And just at a high level, what does that even mean, convolutional? The operation convolution is the process of applying a kernel onto your original image or subsequent feature maps. So a convolution operation is basically a multiplication between your kernel and your image or a feature map, depending on where you are in this journey. Let's think of this as an input image of 36 by 36 pixels. It's a small image, tiny image, 36 by 36 pixels. You are applying a kernel, let's say, to keep things simple, just a 3 by 3 kernel. What does that mean? It's a 3 by 3 matrix with some values in it. And based on the values, you get a certain type of output when you multiply those values with your input image. Some of these kernels are designed to enhance the edges, and we call them edge detection filters. But in summary, a convolution is a multiplication of this kernel onto your image or a feature map. And what happens when you do that? The numbers change, right, in these images. And it's common for us to take that output and do some sort of a, let's say, max pooling, a pooling operation. And max pooling is a type of pooling operation where it takes the maximum number within a given window and then just places that. So by doing that operation, the size of your image is going down all the way down to, for example, where you only have 4 class units. What does that mean? This unit gives you the probability of this being a cat. This one can be the probability of your image being a dog, and so on. So this is how you build a classification engine using your convolutional neural networks. And this is, again, great for classification problems. But what happens? What does object detection mean? Object detection is classification, but multiple times in an image. You can have 20 cats in an image. So you need to identify all these 20 different cats. So you can have 20 cats and 50 dogs in an image. That's a complicated scenario. So you need that many classifications done. So that's what makes object detection a bit complicated. But one way to achieve this is by dividing your image into smaller blocks. So what if you take a large image and say, okay, my cat is about like maybe 50 by 50 pixels. So let me divide the image into 50 by 50 pixel grids. So that's one way of actually dealing with this. But what if you have, for example, in this case, these objects are of different size. This is humans, smaller size. This is humans, large size. If all the humans are of same size, you can just divide them into that size, right? But your objects may be even smaller. If you have a human down there, much smaller. So into how many grids do you want to divide this image into, right? So we can divide them into thousands and thousands of smaller grids, but that's where it gets computationally expensive. So this is why this is not a wise way of performing object detection, like just using pure convolutional neural network approach. This is exactly where RCNN comes into picture. So RCNN does something very similar, what I just mentioned about. Divide the image into number of boxes instead of grids, let's say, and how many? It puts a limit to about 2000 regions right there. Okay, and how does it identify these 2000 regions? So it's not dividing the image into 2000 regions of equal size. It's actually performing something called selective search to extract these 2000 regions from the image. And they call this region proposals. It's actually proposing these 2000 regions. So we can go ahead and look at them, pay closer attention to these 2000 regions. Now, how does it work? Well, the selective search process to extract these 2000 regions, first of all, it generates many candidate regions via initial subsegmentation. So it takes this image and generates many little regions. And then it looks for patterns in these regions and say, hey, these are all similar, so let me group them together. That's what it does as step 2, using a greedy algorithm. And non-maximum suppression is a greedy algorithm. So it uses non-maximum suppression to combine similar regions into larger ones. So it kind of proposes the larger one. So basically step 3 is use the result from this process of greedy non-maximum suppression to make final region proposals. Remember, this is not a fast algorithm. These are all slow algorithms, especially the greedy algorithms. These are slow, but it works. So it's going to use the result from this process to make the final region proposals. Okay, and let me just give you a different graphic that makes this process even more clear to understand. So if you look at this bottom image right there, this is our original image, right? So this image gets divided into 2000 boxes. We are showing only 3 boxes here, but think of it as dividing this into 2000 different regions. Those regions go through it's called warped image regions. It's called warped because the person here can be rectangular. This is even more rectangular. That can be a square. So you need to reshape them into a same size. So they go through a convolutional neural network. So that's why it's called warped image regions right there. So anyway, so you have these 2000 regions. They are reshaped into whatever the size that's required to go through these convolutional neural network. Why are they going through convolutional neural network? What is our goal? At each region that it is proposing, we need to classify it. And also kind of find where the bounding box need to be put around that object. So we need 2 tasks. 1, we need to classify it as what is it? Is it a dog? Is it a cat? And 2, where is it? so we can put the bounding box accurately. To do that, I hope you watched one of my, in fact, most watched videos is about extracting features using VGG16 or a pre-trained VGG16 architecture, and using those features and support vector machines or random forest to create a classification engine. So the feature extractors, instead of manually extracting features, we are using a convolutional neural network, a pre-trained one, as a feature extractor, and then tagging along a support vector machines as a classifier. So that really works very well. And that's exactly what is being done here. So you have a convolute, think of this as VGG16, for example, and the job of this convolutional network is to generate features. And then we need to take the features and classify them using, in this example, support vector machines. So they use support vector machines for classification. What does that give us? It gives us information about whether that object is a cat, a dog, or whatever it is. In addition to that, there is a bounding box regressor that kind of moves the bounding box around and then says, okay, this is where you have the maximum probability of this bounding box to be located. So these are the two things that it actually does after the feature extraction. I hope that makes sense. In summary, an image that regions that are being proposed, the regions go through, in each and every one of these 2000 regions, they go through this feature extractor, classifier, bounding box regressor. Now you can see why this is slow. That's slow because it has to classify 2000 regions per image. 2000 regions, 2000 feature extractors, and classify them. So how does fast RCNN make the process a bit fast? It sends the whole image through CNN. So previously we have different regions identified first, and then they go through the feature extractor. But now the entire image goes through feature extractor, and then in the feature space, you have a region proposal method. So you have different regions right there. Rest of the process is pretty much the same. You resize them and goes through a fully connected layer, and then you have a linear regressor for bounding box regression, and you have your normal linear plus softmax for your classification right there. Yeah, softmax, which means it gives you the probability of what that object is. So that is your fast RCNN. But again, what is the challenge? It's not fast enough. What if you have very large data sets? So this is where faster RCNN comes into picture. Again, go ahead and read the paper, but let me summarize it quickly. The key difference between fast RCNN, in fact, the key piece of technology that also gets used in mask RCNN is the region proposal network. This is what's different. What is that? RCNN and fast RCNN, as we discussed, they use selective search process. Remember the greedy algorithm, non-maximum suppression? That is what's used in terms of proposing the regions, and that algorithm is extremely slow. And faster RCNN right here, it does not use the selective search, and instead it's using something called region proposal network right there. And how does that work? Well, just like fast RCNN, the image goes through first of all, you have an image, it goes through the convolution layers, feature extractor. Yeah, so what do you get on the other side? Feature maps. And a separate network is used to predict the region proposal. So there is another network. It's not using non-maximum suppression, but there is another network that is used in terms of predicting the regions. That network gets trained. Yeah, the predicted regions are reshaped. Now that the regions are predicted, it gets reshaped, and rest of the process is pretty much the same. So region proposal network, an independent network that is not selective search based, is what makes this faster compared to fast RCNN. Okay, if that's great, then what's the primary challenge right there? Well, the primary challenge here is, in fact, it's not a challenge. It's just that this process gives us the bounding box only, and it doesn't give us any information about where it is located at a finer detail. Like, for example, you have a bounding box around the cat. Exactly show me the pixels of where the cat is, like in semantic segmentation. That is the information that it doesn't give, and that can be very useful. This is exactly what mask RCNN does. And that process is called instance segmentation. As you know, UNet, for example, is a great framework for semantic segmentation where it tells you exactly where all the pixels corresponding to a person are in this example. But if you want to identify individual people, individual persons, then there are two ways. You can just draw a line between them, which is you can do that in an automated way using Watershed, for example. But that's not really that accurate. For example, if you look at these two people, this person 4, is behind person 3. That information, with UNet, you don't have that. And with Mask RCNN, you have that information because you have a bounding box for this dude, another bounding box for that person, and then you can assign pixels accordingly. And this is the beauty of instant segmentation. I'm pretty sure you're watching this video because you appreciate the strength of instant segmentation. So how does Mask RCNN work? Again, this is a bit more complicated. Well, it's basically based on faster RCNN, but explanation of ROIAlign, I can already tell you. Let's see if I can do a good job in explaining what that is. But look at other sources if you think you need more information about ROIAlign. But that is the key. That is the key step in Mask RCNN. So in addition to the class label, like is it a cat or a dog, and also a bounding box, it gives us a object mask. That's what Mask RCNN does. So a object mask is nothing but a semantic segmented region, right? So at every pixel, it tells us, okay, that pixel corresponds to this kid. And it uses this trick called ROIAlign. What does that trick do? It locates the relevant areas down to the pixel level. Okay, how does it do that? But first, before jumping into that, first look at this scene. There is a person right there. We know that the class label here is the person and the bounding box is right there. And ROI pooling, it actually gives us a semantic segmented image. And again, let's start understanding ROI pooling. And what is it? I mean, if you think, okay, you heard the term pooling before, I just used it in terms of calling max pooling. A pooling is basically you apply, for example, a box right there, and you say, I want to do something in that box. Max pooling is, okay, this box is covering 4 pixels. Just give me the maximum value within those 4 pixels. And this is how you downsample. So pooling is used to downsample your feature maps. And ROI pooling is pretty much the same thing. So what's the problem then, if that's the case? I just want to introduce a term called stride. You probably know what it is. A stride is by how much you want to move your box to do your pooling. And that box can be moved. That is quantized, right? So what does that mean? I can either move in steps of 1 or 2 or 3, but I cannot move that in steps of 1.3, 1.5. Why do we need 1.3, 1.5 steps? If you look at an image right there, a 7 by 7, for example, and a stride equals to 2, it considers only 6 by 6 pixels. Why? Because if I have 7 pixels, and if I divide that by 3, because we have 3 by 3 right there, we want to get to 3 by 3. Yeah, I want to go from 7 by 7. I'm looking at downsampling. Yeah, I want to downsample my 7 by 7 image to 3 by 3. If I want to do that, my stride should be equal to 2.33333. But because it's quantized, I'm going to round this off to 2, and I'm going to only use 2. And if you use 2 stride, then instead of sampling all 7 by 7, you would be able to only sample 6 by 6. So you're losing that information of this extra pixel right there. So I hope that makes sense. A different way of, so that is the problem. What is the solution? How did Mask RCNN actually solve this? So think of this as this 5 by 5 grid right there. So let's understand how ROIAlign actually works. So this is a 5 by 5 feature map, okay, in the dashed lines right there. And now this is the region proposal. So this red region is the proposed region. So how do we perform a max pixel or pooling within that region? So we have 4 bins right there, and we need to get, for example, within this bin, like right here, I want to get max or do some sort of a pooling from my feature map right there. How do I do that? Because this is not correctly aligned with your image. So do I take pixel value from here? Or do I take a value from here, from this grid? Do I take a value from this grid or this grid? So how do we get there? So to do that, do I have that in text? Yeah. So 4 points in each bin. So this is one bin, right? So 4 points are sampled. And at this point, what is the value? How do you get the value? So when you have like something that falls in between 2, 3, 4 different things, how do you get like an average of all of these, like the value at that point? You do some sort of a math to get this based on its proximity to the neighborhood. That's exactly what it's using here, bilinear interpolation. This is very similar to what happens when you upscale or downscale an image. You do some sort of an interpolation, and bilinear is a very common form of bilinear interpolation. That's exactly what they are doing right here. Bilinear interpolation gives them the value, weighted value, compared to when you take care of all of these, when you incorporate the information from all of these other pixels. So this is exactly how ROIAlign works, and I told you I either succeeded in communicating about what ROIAlign does, or I failed completely at it. If you think I failed at that, go ahead and look at other sources to figure out exactly what this is. But I guess that's the extent of my explanation. Okay, so now just to finish this off, you have a scene like this. A semantic segmentation colors every pixel. So every pixel in the bottle, every pixel in the cube clearly gets assigned. So semantic segmentation is great in many situations, but what if you have two objects that are one behind each right there, and in semantic segmentation you don't have that sense. It doesn't know that this is object number 1 and that's object number 2. So this is exactly where our object localization, like RCNN, comes into picture. RCNN says, hey, you have like 3 cubes right there, and you have like an like a cup right there, and you have a bottle right here. But what if you want the information that's a combination of your object localization and semantic? This is exactly what instance basically gives you. And one class competes at every pixel. So at every pixel, one class is competing. So the segmentation process becomes easy for the network. And of course, masks of all objects are calculated at every pixel, but it considers one at a time. So that's why the segmentation process is a bit easy for mask RCNN, and this is the mask part of it. Okay, so finally, how do we do the coding of this mask RCNN in Python? Well, we don't have to do anything because there are a lot of smart people out there who actually came up with the original, for example, Keras version of mask RCNN, and that uses TensorFlow 1.0, and then someone else said, well, now we are using TensorFlow 2.0, so let me convert everything into 2.0, and you'll find various libraries where people change that original one into 2.0 and so on. So this is what makes it even a bit more complicated. Instead of contributing in towards one project, now you have like many forks, and it's tough to find out which one works the best. So let's do that exercise in the next tutorial. Let's see which one. Let's actually pick one and download it and go ahead and install. So let's meet in the next video, guys. And again, until then, fill the gaps in your knowledge about mask RCNN by looking up specific topics, whether it is ROIAlign or the mask part of the mask RCNN. But I hope at a high level you understand exactly how the object are identified objects are segmented in your images using mask RCNN. So let's go ahead and meet in the next video. Like this, subscribe, and have a nice day.